Hello everybody, welcome back to the online course on embedded system design, verification and test. So, till now we have seen about the verification and we have discussed about the CTL model checking. Today we are going to introduce one new tools called binary decision diagram, which will help us to represent our system in a compact way, and that same tools or technique binary decision diagram will be used for verification purpose also. So, we are going to discuss about the binary decision diagram today. Now, we have discussed about the model checking algorithm, and after discussing or after going through the model checking algorithm, what we observed that the complexity of the model checking algorithm is polynomial in the size of the state machine and the length of the formula. Okay. So, size of the state machine. Okay. Again, size of the state machine depends on the number of control variables or number of working variables that we have in the system. So, the inherent problems with the model checking algorithm is the state space explosion problem. So, to control this state space explosion problem, BDD or binary decision diagram is going to help us up to certain extent. Now, what is this state space? You just see that if we are having 3 variable ABC, say control variable or whatever it may be, then we know that we are having total 2 to the power 3, total 8 different combination of ABC. They varies from 0, 0, 0, 0, 0, 1 to 1, 1, 1. So, total 8 possible combination. So, these possible combinations are generally treated as a state of the system. That means, state of the system is altogether 8. That means, I can say that this is my state S 0, where the values of the signal variable A, B, C equal to 0. That means, A equal to 0, B equal to 0, C equal to 0. Similarly, sir, from S 0 we are having a transition to say S 5. Okay. In case of S 5, I can say that the values of the control variable is A equal to 1, B equal to 0 and C equal to 1. So, that values of the control variable basically talk about the present state of the system, and if you look into this scenario, then we are going to have total 2 to the power 3, which is equal to 8 different states. Now, for that, if I am having an n control signal, then total number of state space or the complete state space will be your 2 to the power n. Okay. So, if n is 10, we are going to get 1024. If n is 11, we are going to get 2048 like that. Okay. So, you just see, if we are going to increase the control variables, number of control variable, the number of states are also going to increase, but in some system all state may not be reachable. What does it mean? That means, all configurations are not valid for that particular system, and we basically concern about the reachable state space. Now, in that particular case, say in my design, due to some constraint, I am increasing the control variable from n to n plus 1. In that particular case, the total number of states will be 2 to the power n plus 1. So, that means, the state space explosion is exponential in nature. Okay. So, if you look into that model checking algorithm, it is nothing but the graph traversal algorithm. Okay. And the system is represented with the help of crypto structure, which is a graph, and we are going to apply our model checking algorithm on that particular models. So, it is nothing but a graph traversal algorithm. So, if we are having more number of nodes, then algorithm is going to take more steps, though it is polynomial in time. Okay. But still, for more states we are having more problem, because we have to have more memory space in our machine also to encode all the states. Now, to cater or to contain this particular problem, now we are going to look another tools, another approach to represent our system, which is known as your BDD, binary decision diagram. So, in a nutshell, how we are going to talk about the BDD, or what is the basic principle of the BDD. So, BDD basically based on recursive Shannon expression. So, you can express all the Boolean expression, or you can expand it with the help of Shannon expansion. So, Shannon expansion is given here like that: if f is a function of some variables, then it can be expanded with the help of the participating variable. So, x is a participating variable for this function f. Then f can be expressed as f is equal to x f of x plus x bar f of x bar. So, f of x basically says that it is the functional value when we are going to put x equal to 1, and f of x bar basically say it is the functional value when we are going to put x equal to 0. So, if x equal to 1, then 1 into the values of the function with respect to x equal to 1. When x equal to 0, then x bar become 1 dot functional values of the function with respect to the variable values x equal to 0. That means, we are taking care of all the possible combination when x equal to 0 and x equal to 1. So, this is the basis of our Shannon expansion, and to construction of the BDDs, we are going to take help of this particular Shannon expansion. Now, what is an BDD? It says that it is a compact data structure for Boolean logic. That means, if we are having any Boolean expression, it can be represented with the help of BDD. Again, the state space that we are having can be encoded with the help of a Boolean expression, Boolean logic expression, and that Boolean logic expression can be converted or can be represented as a BDD. So, it is a compact data structure for Boolean logic. And what is the advantage of this particular BDD representation? It says that we are having a canonical representation of an expression, of a Boolean expression, if the representation is your reduced ordered BDD, reduced ordered binary decision diagram, ROBDD. At that time, we are going to get the canonical representation, and what does it mean? That means, we are going to get an unique representation or unique BDD for a given Boolean expression. We are going to look into it, we are going to discuss about it, but you have to be very careful about it. It talks about a reduced ordered BDDs. So, if it is a simple BDD, then we may not get canonical representation. So, what does it means? We may have several structure for the same Boolean function, but if it is ROBDD, we are going to get a unique representation. Now, the Shannon expansion, just I am going to say how the Shannon expansion is going to give us the proper functional value. Already I have explained that we have taken care of both all the possible cases of x is equal to 0 and x is equal to 1. Now, in that particular case, you just said that I am taking a small example, f is equal to a c plus b c. So, this is a Boolean expression having 3 variables a, b, c. Now, if a bar, when I am going to get a bar, if I take the value of a equal to 0. That means, if I put a is equal to 0, then this f a bar will become b plus b c, because 0 into c will become 0 and 0 plus something is equal to that value. And similarly, if I put f a, it is nothing but the functional value at putting the value of a equal to 1. So, in that particular case, since a equal to 1, we are going to get c plus b c. So, this is the x values functional value when we say x equal to a. Now, what is the given function? It is saying that f is equal to a into f a plus a bar into f a bar. That means, we are going to get a into f a, that means, a into b, c plus b c, and a bar into f a bar is a bar into b c. Okay. So, now, if I expand it, then what I am going to get? A c plus a c plus a b c plus a bar b c. So, this is equivalent to a c plus, if I take a bar common, then I am going to get b c plus I did a mistake. So, if I take b c common, then I am going to get a plus a bar and a plus a bar is equal to always 1. So, I am going to get a c plus b c. So, this is the given function. So, this given function can be expanded with the help of this particular Shannon expansion. We have expanded it with the help of the variable a. Similarly, we can look for the expansion of this particular function with respect to say variable b or c, and eventually the Shannon expansion is going to retain the given function. So, this is the basis of our BDD construction. So, we are using Shannon expansion to construct our BDD. Now, first before going to BDD, we are going to talk about BDT, binary decision tree, and from that we will say how we are going to get the BDD. So, what is a BDT? The representation is like that: binary decision tree are trees whose non-terminal nodes are labeled with Boolean variables x, y, z, and whose terminal nodes are labeled with either 0 or 1. This is one thing. So, it is having non-terminal nodes. I can say some of the non-terminal nodes like that. So, if I am having a function of a, b, c, then this non-terminal node will be either marked with those particular variable a, b, and c. And along with that, it is having a terminal nodes. So, terminal nodes is denoted by this particular box, and it have the values either 0 or 1. It says that if it is 0, that means the functional values is 0 with respect to this particular evaluation, and if it is functional values is 1, then we are going to say this is the terminal node 1. So, now each non-terminal nodes are having two edges, one is dashed line and second one is your solid line, and dashed line represent 0 and solid line represent 1. What does it mean? Say A is a non-terminal node. So, we can say that we are having a dashed line to this particular non-terminal nodes B. So, in that particular case, since this dashed line is indicated that this is my value 0, or I can say that evaluation of this particular variable at that particular point is 0. Similarly, it is having another outgoing edge which is my solid line. So, it says that the evaluation of this particular variable is 1 if I am going to traverse this particular part. Okay. So, what we have in BDT, binary decision tree, we are having nodes, two types of nodes, terminal nodes and non-terminal nodes. We are having edges, solid edges and dashed. Solid is going to indicate that the evaluation is 1 and dashed is going to indicate that the evaluation is 0. Again, terminal nodes is going to give me, or terminal nodes are going to give us the functional value for 1 or it may be 0. So, these are the component of BDT. Now, look for a simple example. Say I am taking the same function f is equal to a b plus b c. So, we know that if we are having any Boolean function, that can be represented with the help of truth table. So, this is the functional or the functional values of the given Boolean function. So, it is said that if a is equal to 0, b is equal to 0, c is equal to 0, then a c will become 0 and b c will become 0, and eventually my functional value is 0. If a, b, c are 1, then a c, a dot c will give me 1, b dot c will give me 1. So, 1 plus 1 will give me 1. So, this is the truth table representation of Boolean function. Now, when I am going to draw the binary decision tree, for every variable you have to see the decision whether values of that variable is 0 or 1. So, that is why that for variable a, I am having either variable a can take value 0 or it 1. So, after getting the values of a, now we have to look for the values for b. Again, the valuation for b may be either 0 or either 1. After taking c, after taking the decision on b, we are going to take a decision on c. Again, c may be either 0 or either 1. Now, if I traverse say a equal to 0, b equal to 0 and c equal to 0, in that particular case I know that functional value is 0. So, this is the terminal node. So, when a equal to 0, b equal to 0, c is equal to 0, my functional value is 0, it is coming to this particular terminal node 0. Similarly, if I say that a equal to 0, b equal to 0 and c equal to 1, then again my result is 0. if I say that a equal to 0, b equal to 1 and c equal to 1, then my functional value is your 1. A equal to 0, b equal to 1, c equal to 1, my functional value is 1. So, it is terminated at this particular one. Now, this is the representation of BDT, but if I just look into that BDT, we are not getting any advantage or benefit, because this truth table is also exponential in nature. Now, for 3 variables we are having 8 entries. Now, if I increase one more variable, say if we are going to work with 4 variables, then we will be having 16 different entries. So, it is increasing exponentially. So, similarly, if I look into this particular BDT, here also I will find that if I am working with 3 variables, then I am having 3 levels of non-terminal nodes, because you have to see whether these are zeros or 1. Now, if I have one more variables, then what will happen? I am going to get one more level of non-terminal node, and after that I am going to get the terminal node. So, for 4 variables, the number of terminal nodes will be your 16 and it will have 4 levels. So, again the BDT is exponential in nature. Just for construction purpose we are showing it, but just with BDT we are not getting any advantage. It is still having that nature of exponential expansion. Now, from BDT, now we can talk about the binary decision diagram. It is similar to BDT, except that BDT is a tree, but BDT is a graph, or it is a directed acyclic graph, and other notions are similar. We have terminal nodes, we have non-terminal nodes. Okay. Non-terminal nodes are marked with the functional value 0 or 1. Non-terminal nodes will be marked with the variables, and every non-terminal nodes having 2 outgoing edges. Dashed outgoing edge indicates that the value of that particular variable is 0, and the solid line indicates that the value of that variable is 1. So, instead of tree we are having a graph. It is a DAG, directed acyclic graph. So, we can now see how we can construct a BDD. Now, when we talked about the BDD, then we are having 3 primitive BDD. We are having 2 constant values 0 and 1. So, these are basically terminal nodes. So, B0 is the BDD for constant 0 is generally represented with B0, and it is a terminal node with the value 0. Similarly, B1 is the BDD representation of constant value 1, and it represented with this particular terminal node 1. And similarly, for any variable x, we have this particular representation Bx, it says that BDD representation of the variable x. So, we know that since it is a Boolean variable, it can take 2 values, either x equal to 0. So, it is going to indicate with the help of this particular dashed line, and the value of x is 0. So, it is terminated in this terminal node, and similarly x can take 1. So, it is represented with this particular solid line, and this is terminated at 1. So, these are the primitive BDD that we have in our system. Now, just say we are going to look for the construction of the BDD. So, if we are going to have the same function f is equal to AC plus BC, then f a dash is equal to BC, and we said this is the function 0, and when f a is equal to 1 or a is equal to 1, then f of a equal to 1 is equal to c plus BC, which is I am saying that this is the function h, this is the function g. Now, what it says that now a can have value 0. When a is having value 0, that means we are coming to another terminal node with the evaluation of 0, and in this particular non-terminal node, it is going to represent the functional value of g, and what is g? G is nothing but BC. Similarly, when the values of a is equal to 1, then we are coming to this particular terminal nodes, okay? And what equation or Boolean expression we are representing in this particular terminal node? It is the function h, which is c plus BH. Now, you just see that root nodes is going to represent the given function f. Now, after knowing the evaluation values of that particular variable which is indicated in this particular starting node, and here we are talking about a. So, a can have either 0 or 1. When we are having a equal to 0, then we know that the functional value is b c, we are indicating it with g. So, this particular node is going to talk about the valuation of the function g. Similarly, this one is going to talk about the valuation of the function h. Now, after coming to this particular point, now we are having functions of two variables b and c. Now, you have to see the evaluation of the function with respect to b and c. Now, when for function g, we are talking about that looking at the evaluation with respect to b. So, this terminal node is b, and when it is your b equal to 0, that functional value is 0. So, we are getting this particular dashed s and coming to this particular terminal node 0. When b equal to 1, then the functional value is c. So, we are coming to this particular node, and what is the function over here? We are going to have the variable c. Similarly, if I am going to now look for the function h, if function h, if b is equal to 0, the functional value is c. So, it is coming to this particular terminal node c. When c plus b c, when b equal to 1, again we are going to get c. So, with 1 also it is coming to c. Now, the remaining function that we need to evaluate is having the constants of variable c only. Now, we know that if c is equal to 0, the functional value is 0, if c is equal to 1, then the functional value is 1. So, now finally, we are going to get this particular construction or BDD, c equal to 0, it stands to 0, c equal to 1, it is at 1. So, when we use the Shannon expansion, then the BDD representation of this function is this one. So, it is having 4 terminal nodes and 4 non-terminal nodes and 2 terminal nodes. Now, say same function we are having. So, for BDD representation, we have this representation where we are having 8 terminal nodes and 7 non-terminal nodes. When you use the Shannon expansion, we say that we are getting 2 terminal nodes and 4 non-terminal nodes. So, just here I am trying to give an idea that if we use BDD, then for most of the Boolean function we are going to get an compact representation. Okay, we will see in the discussion. Now, we have when we are having these things, now it may have a scope to further reduce this particular BDD or BDT. Now, we will see what are the reduction rule. So, first reduction rule, it says that eliminate the duplicate terminals. So, because the terminals are having either values 0s and 1, we are having multiple terminal nodes and multiple terminal nodes with values 0 and with values 1. So, they can be merged, we can represent all zeros by 1 terminal nodes and 1 all 1 by 1 terminal node. So, that is why you said if this is the BDT, then what will happen? I can have such type of construct where all zeros are merged together and all ones are merged together. So, we are getting these things, and accordingly we are redirecting all those particular edges, which is going to conform to the original redirection, original evaluation or original valuation. So, this is the rule 1. If we are having multiple terminal nodes, we can merge them together. Okay. So, BDD reduction rule 2, it says that eliminate the redundant nodes. So, what is a redundant node? So, for this particular node, you just see, so this is A, that node A. What will happen? If I take the valuation of A is equal to 0, it is coming to this particular terminal node, non-terminal node B. When I take the valuation of A is equal to 1, again it is coming to that same non-terminal node B. Now, at non-terminal node A, we are giving the valuation of function f, and f b we are giving the valuation of function g. So, you just see whether it is a equal to 0 or a equal to 1. In both the cases, we are going to evaluate the function g in the next level. So, that means decision on a is slightly redundant, means it is now independent of this particular variable a in this particular evaluation. So, now since for both a equal to 0 and a equal to 1, we are having the same function g. So, we may eliminate this particular redundant node. So, checking the values of a is redundant at that particular point. So, it says that elimination of the redundant nodes. This is the second rule. And rule 3 talks about the merge duplicate nodes. Now, we have to see what are the duplicate nodes and how we are going to merge them. So, node must be unique. So, in this particular case, just consider this particular scenario. In this particular non-terminal node, we are evaluating the function f 1, and in this particular non-terminal node, we are evaluating the function f 2. Okay. Now, when a equal to 0, we have to evaluate the function g in node B, and when f is equal to 1, then we have to evaluate the function h in node C. Similarly, if a is equal to 0, we have to evaluate the function g, and a is equal to 1, we have to function h. Now, just see the nature of these two non-binary nodes are almost similar. Okay. Or I can say it is same, because for a equal to 0, we are going to have the same function g. For a equal to 1, we are having the same function h. So, in that particular case, what will happen? We can merge these two nodes to one node, and after merging it, what will happen? That outgoing edges are having the similar behavior, but all the incoming nodes, these two nodes will be the incoming nodes to this particular merge node A. Okay. So, we can merge duplicate nodes or duplicate non-terminal nodes. So, this is the BDD reduction rule number 3. So, these 3 rules can be used to reduce our BDD. So, first rule can be first rule will be used only once, because we are having all the terminal nodes at the leaf level. All zeros will be merged to one 0 nodes, and all ones will be merged to one node. So, it will be applied only once, but rule 2 and rule 3. So, removal of redundant nodes and removal of duplicate nodes can be applied several times, because first you remove one redundant nodes, then what will happen? We are getting some nodes which can be merged together. After merging some of the nodes, you will find that again we are getting some other nodes as a redundant node. Now, we can remove that redundant node also. So, they can be applied several times until and unless we could not apply any other rules for this reduction. Okay. So, in that particular case, what will happen? If I cannot further apply the rule 2 and 3 to the BDDs that we have achieved, then that BDD is known as the reduced BDD of the given function. Now, for this particular function f a c plus b c, we know that this is the BDT, and this BDT can be first merged this all zeros to one node and all ones to another node. Now, after having these things, now you observe what can be done. Now, here you will see their observation, these 3 nodes, okay. They are having the similar behavior, but other C nodes is having different behavior, because for both 0 and 1 it is 0, but for these 3 nodes, for 0 evaluation is 0, for 1 evaluation is 1. Okay. So, this is slightly different. So, now what we can do? We can merge those particular node, and we are coming to this particular point. Okay. Now, after this, what we are getting? You just see Now, we have merged duplicate node. Now, we are going to get some redundant nodes. What are the redundant nodes? These two are redundant nodes, because you just see for both b equal to 0 and b equal to 1, it is coming to that node C. Here also for c equal to 0 and 1, the functional value is 0. So, we can remove those particular redundant nodes. Now, finally, we are going to get this BDD. This is the representation, BDD representation of the given function, and it is the reduced one. So, we said this is the reduced binary decision diagram, because you cannot further reduce this particular BDD. So, we are taking a particular function, and from BDT we are coming to RBDD, reduced binary decision diagram. Now, the same function I think we have constructed with the help of Shannon expansion. So, in that particular case, when I apply this particular Shannon expansion, we get this particular structure. Okay. Now, here we will find that this node B is a redundant node, because for both B is equal to 0 and 1, I have to look for the evaluation of variable C. So, that B can be removed. So, what will happen after removal of this particular redundant node, I am going to get this particular structure. Now, we just see whether you are using BDT or Shannon expansion, we are going to get the same reduced BDD. Whether always the reduced BDDs are having the same structure? My answer is no, because it depends on some other criteria also. We will see that criteria also, what is that particular other criteria. But anyway, whatever we have achieved, it is the reduced BDD, because we cannot further reduce it. That means, we cannot further apply the rule removal of redundant nodes and merge of duplicate nodes. Okay. So, this is the reduced BDD, and for both the approaches we have achieved the same structure, same BDD or same reduced BDD, and why you have got the same BDD, it will be clear to you in that particular discussion. Okay. So, what is a reduced BDD? Already I have said that a BDD is said to be reduced if none of the reduction rule R1 to R3 can be applied, that is no more reduction are possible. So, here we cannot apply any more rules. So, this is the reduced BDD of the given function. Now, when we discuss about the BDDs, or when we have given the definition of the BDDs, here we are not mentioning anything about the ordering of the variables, that means in which order the variables may appear, and occurrence of the variable. How many times a variable can occur in the BDD? Say x is a variable, then how many times x can occur, or in how many levels x can occur. We are not mentioning anything about that issues while defining the BDD. So, with respect to the given definition of BDDs, we have to accept this one also in BDD of some given function. Okay. Now, in this particular case, you just see here I am having 3 variables x, y, z. So, first I am having the evaluation of x, then when x equal to 0, I am having the evaluation of y, when x equal to 1, I am having the evaluation of z. Okay. With respect to z, when z is equal to 0 and z is equal to 1, again x is appearing over here. Okay. So, as per the definition of BDD, this is a BDD, a representation of the valid function. Now, if you do not restrict the occurrence of a variable in a path, then we are going to face some problem. So, due to that problem, now we have to have the notion of those particular path. We are having now 2 kind of evaluation path. One is known as your consistent path and other one is your inconsistent path. So, when we are going to consider the evaluation path, always you have to consider the consistent evaluation path only. We have to ignore the inconsistent evaluation path. Now, what path will be the inconsistent one? If you look into this particular example, you just said in this particular evaluation, it says that x equal to 0. when y equal to 0, we are coming to this particular point. Okay. Now, when we are taking a decision on y, again we are relooking into the evaluation with respect to x. So, it says that if x is equal to 0 over here or x equal to 1 over here. So, in that particular case, when we are coming to this particular non-terminal nodes, you just see that already we have taken a decision on x, this is x is equal to 0. Here again I am taking a decision or looking for the evaluation of x, it is x is equal to 0 and x equal to. So, if I follow this particular path, then I can say it is a consistent path, because in this evaluation the values of x is treated as 0. But if we consider the other path, then this path is treated as an inconsistent path, because in a particular evaluation the variable values will be either 0 or 1. It cannot have both the values. So, in this particular case, what we are going to see, at some point of time we are saying that x is equal to 0, at some point of time saying x is equal to 1. Okay. So, in that particular case, this will be the inconsistent part. So, when I am going to look for the functional values of the function that is represented by this particular BDD, then we have to ignore this particular inconsistent parts. There may be several inconsistent parts. So, we should not consider those particular inconsistent parts. For evaluation of this particular function or evaluation of this particular function, use only consistent part. Okay. So, this is the issues of consistent part and inconsistent part in an BDD. So, to avoid this particular inconsistent part in BDDs, now we are coming to the notion of ordered BDD. Okay. This is called ordered BDD. And what is an ordered BDD? In an ordered BDD, we are going to follow a particular order of the given variables. Okay. We are having a set of variables, say x 1 to x n. Then we are going to create an order list of variables without duplicating or without duplications. That means, all variables are unique, and we are going to construct a BDD and let B be the BDD, all of whose variable occurs somewhere in the list. Okay. So, in BDDs this variable will occur somewhere in the construction. Now, we say that B has an ordering B 1, B 2, B x up to x n, B has an ordering x 1, x 2, x n if all variable labels of B occurs in that list, and for every occurrence of x I followed by x j along any path in B where I is less than j. Now, what it says, if I am having these non-terminal nodes, whatever part you are saying that if this is the ordering is your this one x 1 to x n, if it is your x 1, this is your x 3, this is your x 5, x 4, then x 5, like that. So, we can have something like that. So, in that particular case, we are coming over here. Now, this what is the label of this particular node? It must follow this particular ordering. So, in the ordering it says that already we have using x 1, x 3, x 4, x 5. Till now, we have not used x 2, but the label of this terminal node cannot be x 2. It may be after x 5, it may be either x 6 or maybe x 7, x 8, like that. If the variable x 2 is present in this particular function, then x 2 have to come somewhere over here, which appear before x 3 and x 4, or maybe x that I greater than 2. So, this particular ordering we are going to maintain while constructing the BDD. Then we say this is a ordered BDD, and what is the order? It is x 1, x 2 to x n. Now, impact of the chosen variable ordering. Now, we are talking about the variable ordering. Now, when we are going to use this particular variable ordering, what ordering you are choosing depends on that we are going to get different structure. So, structure is not unique if it is our order are different. So, in this particular case, just considering a simple example that we are considering this particular Boolean expansion or say Boolean expression. So, in that particular case either I can have a ordering like that x 1, x 2, x 3, x 4, x 5 like that, or maybe we can consider this particular Boolean ordering, variable ordering x 1, x 3, x 5, then x 2, x 4, x 6. That means all odd subscribed are coming at the beginning and then all the even subscribes are going. But here we are using this particular notation. So, in that particular case it says that if I use this particular ordering, then total number of nodes will be your 2 to the power n plus 2, but if we use this particular variable ordering, that total number of nodes become 2 to the power n plus 1. So, there is a tremendous impact of the variable ordering, but to find out the proper variable ordering to get the optimal BDD representation of given function is a hard problem. We do not have the proper algorithm, but we use some heuristic to contain the size of the BDD. Okay. So, depending on the variable ordering, the construction is different and number of nodes will be different. So, in this particular case, one is saying that it is polynomial, but second one become exponential. So, this is the construction, just I am saying you can check it. So, if this is the given function of 6 variable and the variable order that I am using x 1, x 2, x 3, x 4 like that, x 1, x 2, x 3, x 4, then this is the BDD representation of this particular function. But same function, if I use the ordering x 1, x 3, x 5, x 2, x 4, x 6, then we are getting another representation which is having more number of nodes, which is an exponential in nature of the number of variables. So, variable ordering is also have importance while constructing the BDD. Okay. Now, we have seen reduced BDD, we have seen ordered BDD. Now, if we are having an ordered BDD and if it is a reduced one, then we say this is your reduced order binary decision diagram and we write ROBDDs. Okay. So, in case of ROBDDs, the variables are following a particular variable ordering, and secondly it is a reduced one, we cannot further reduce it. Then in that case we are going to say this is your ROBDD. So, now what is the properties of ROBDD? The reduced BDD or ROBDD representation of a given function is unique. That means, if you represent a given function with an ROBDD, reduced order binary decision diagram, then always you are going to get an unique representation. So, that is why we say that ROBDD is a canonical representation of a given function, because in case of canonical representation we are going to get an unique expression. So, here also the BDD representation is unique for reduced order binary decision diagram. Now, secondly it says that what it says that let B 1 and B 2 be two reduced order BDDs with computable variable ordering. So, what is that computable variable ordering? That means, whatever variable ordering we are using for B 1, same variable ordering we are using for B 2. Okay. Then in that particular case, we are having an identical structure. It is an 2 BDDs we are saying, it is a representation of the same function and both the BDDs are having computable variable ordering. That means, both are having the same variable ordering, then the structure is same. The order in which we apply the reduction does not matter. So, I am saying that I can apply the reduction rule first, removal of redundant nodes, then the merge of similar nodes. Okay. But we can apply in the reverse way also, but finally we are going to get the same BDDs. So, that is why since it is the representation is unique, so we are going to say it is a canonical form if we are going to use ROBDDs. We can consider now two defined function f 1 and f 2 and say B 1 is having a B 1 is the BDD representation of f 1 and B 2 is the BDD representation of the Boolean function f 2. If the ordering of B 1 and B 2 are said to be computable, if there are no variable x and y such that x come before y in the ordering of B 1 and y comes before x in the ordering of B 2. Okay. So, that means they should not have different variable ordering. In that particular case, we are going to say that this is being the computable. Okay. That means these two BDD representation of these two functions are computable if both of the BDDs are going to follow the same variable ordering. Now, we are having several operations actually. Now, how we are going to do with the help of your BDD? Say I am having a function f, say a b plus c, and I am having another function say g, where it is your say b plus a c. Then what will happen? Always I can perform the operation say f plus g, or I can perform f dot g like that. So, these are the Boolean operators that we have. Now, we are going to get some representation, some function over here, and here you know that this function a b plus c can be represented with the help of an BDD. I said that this is the BDD representation for function f is your b f. I say it is better to write. Similarly, the BDD representation of the function g is b g. Okay. Now, can you perform this operation directly on the BDDs? One way is to you perform the operation, get the Boolean expression, then represent that Boolean expression with the help of an BDD. Okay, this is one approach, but if already we have the BDD construction, can we use those BDD to get this particular function f plus g? That means, we can say this is maybe b f plus b g. Can you get the similar effect? Yes, we have a method for that, where we can perform the Boolean operation on BDDs, and this algorithm is known as apply. Apply is the common method, and this apply is having three parameters: apply, OP, BF, BG. So, BF is the BDD representation of function f, BG is the BDD representation of function g, but in that particular case both BDDs should have computable variable ordering. If the variable ordering is different, then we cannot use this particular apply method. So, in that particular case we can use this apply of BF, BG. Now, if I want to perform this particular f plus g, then what I can say? Apply, I can use this particular algorithm apply plus BF and BG. Okay. So, this whatever BDDs we are going to get, this BDD is going to give us the BDD representation of this particular operation f plus g. But you have to remember that it has both the BDDs must have a computable variable ordering. It may be reduced or it may not be reduced, but they have to be ordered, and secondly both the BDDs must have the computable variable ordering. Okay. Now, after application what will happen? We are going to get a resultant BDD. So, this resultant BDD will also have the same variable ordering, whatever variable ordering we have for BF and BG, but the resultant BDD may not be an RO BDD. Okay. So, we are talking about the order BDD, or I can talk about RO BDD. Say BF is the RO BDD representation of function f, and BG is the RO BDD representation of x. After performing this operation, say apply plus BF BG, the resultant BDD will be your ordered BDD. That means, that resultant BDD is also going to have the same variable ordering that we have for BF and BG, but it may not be the reduced one. So, after that what you can do? You can apply this particular reduction method to get the ROPDD. Okay. So, this reduce algorithm can be implemented because we have the rules, 3 reduction rule. So, we are having an implementation of that particular reduce algorithm also. Okay. Now, how apply algorithm works? Okay. So, the apply algorithm works on the Shannon expansion. Okay. So, if I am using 2 function f and g, now this is the Shannon expansion of f and this is the Shannon expansion of g. Now, when we are going to perform any operation, then you just see that you can have these components separately and these components separately. Here it says that evaluation of function f and g with respect to x equal to 0, and here it says that evaluation of function f with respect to x equal to 1. So, finally, these 2 components are coming over here and other 2 components are coming the other side. Okay. So, in BDD you just see that x equal to is 0 is having some evaluation, x equal to 1 is also having some evaluation. So, this is say BF and say this is your BG. So, this is the construct and say if both are that variable x, then you just see that for x equal to 0, we are going to have this particular part. For x equal to 1, we have this particular part. Okay. So, now we can use apply algorithm on 2 given BDDs, and that apply algorithm works with respect to Shannon expansion. So, whatever resultant BDD we are going to get, that will give us the correct evaluation of the operation. Now, already I have mentioned about these things. Now, how algorithm works? So, if RF and BG are terminal nodes with labels LF and LG respectively, compute the value LF of LG and the resultant OBDD is B0 if the evaluation is 0 or if it is B1 otherwise. Now, you just what does it mean? So, I am having some construct. Finally, say this is the x equal to 0, it is 1. Similarly, this is BF, BG. So, this is also say I am going to say x and say this is say 0. Now, what it says when both RF and RG are terminal nodes. So, this is RF and RG. If both are terminal nodes, then you apply the operation 1 of 0 on the terminals, okay, and you create a terminal nodes. Depending on this particular operation, say if it is a plus operation, then 1 plus 0 will give me 1. So, the terminal node will be 1. So, if it is a terminal node, either we are going to get the BDD B0 or BDD B1 depending on the result of the operation. Similarly, now for the remaining cases, so if both are terminals, it is fine, but what are the remaining cases that we are having? So, if both nodes are your xi node, okay. So, that means both are having same node xi and we are going to perform operation over here. So, in that particular case, the resultant BDDs whatever we are going to get, we will create an xi node and this xi may have either 0 and 1, 0 and 1. So, in that particular case, it says that we are going to create an xi node and with the dashed line with apply of low of FR and LO of RG. So, this is a node RF and RG, then and a solid line with apply of high of RF, high of R. So, in this particular case with dashed line, we are going to get this particular node with solid line node. So, what is the functional value over here? It says that apply operation low of RF and low of RG. That means, this is basically low value and this is the low value. You just see what we are having over here, and accordingly we are going to construct the node, and this is the high, okay, high. Accordingly we are going to do this thing. So, what is low and high? Basically this is a two function low n and high n. Given a non-terminal nodes n in a BDD, we define low of n to be the node pointed to via the dashed line from n. Similarly, high n is the node pointed to via the solid line from n. So, we are going to have those particular low and high, and accordingly we are going to perform the operation with respect to these two nodes here, okay, below this particular point. We will see these things. Now, similarly, now another case, what will happen? We are having something that here we are having an Xi node, which is called say RF, and I am having an Xj node in your RG, say this is your BDD BG and say BDD BF, where I j is greater than I, because both of them are going to follow the same variable ordering. So, what does it mean? So, when we are coming to this particular point, from starting we are getting some Xi node, and from starting we are getting some Xj node. So, when we are coming to this particular point, what does it happens that this is may not have, since j is greater than I, before that, that means we do not have any Xi node. Okay. So, that means this in this particular evaluation part, it may be independent of Xi node. So, that is why that Xi and Xj is coming together. So, if j is greater than y, then what will happen? Since it is independent of Xi, because we are getting Xj along with Xi. So, the resultant function will depend on Xi. So, we are going to create an Xi node, and how we are going to create Xi node? For that dashed line. So, here I am having dashed line and solid line. We apply low of RF and RG, and for solid line of high of RF and RG. That means, since here we remain in this particular jth node only, because we have to see how it is going to behave when I am going to get this particular Xj node in this particular BDD. Okay. So, that means, since it is independent of Xi, so we keep or remain with Xj in this particular BDD, but we will make an progress in this Xj in a simple manner, I can say like that. So, that is why low of RF and RG, high of RF and RG. So, this is the scenario that we are having, and this is the reverse of the previous one, when I am saying that RG is the Xi node and RF is a terminal node or Xj node. It may be a terminal node or it may be an Xj node also, because terminal node will come far below down in the leaf nodes only. Okay. So, whatever scenario we are having, this scenario is the reverse of the previous one. That means, one is independent, BF is independent of Xi. So, here I am going to get a Xj node in BF and Xi node in your BG. So, this is the reverse of this thing. So, that is why here we are saying that we call it Xi node, where it is low of RG and RF, high of RG and RF. That means, RG is progressing, but RF is remains at that particular point. So, this situation, this condition is the reverse of the previous one. So, if you see, we might have taken care of all possible cases. One is if they are terminal nodes, okay, fine. Secondly, they are having the same Xi node, and third one is they are defined. One is Xi node and other one may be xj node or terminal node. Okay. These are the possibilities that we are having when we are going to construct the BDDs while applying this particular apply method. Okay. Now, this is a simple example, you can work, you may work with it, just I am giving the idea. Say here we are having two BDDs, say this is on BDD 1 and BDD 2, and it is having variable x 1, x 2, x 3, x 4, and say variable ordering also x 1, x 2, x 3, x 4, because x 1 is coming first, then x 3, x 4, here x 1, x 2, x 3, then x 4. So, in this particular part we are following these things. Now, both are having the computable variable ordering, both the functions are based on this variable x 1, x 2, x 3, x 4. So, now we can apply our apply algorithm over here if I am going to perform this particular operation. Now, how we are going to proceed? It is a recursive call and we will always start from the root node. Now, both the nodes are your x 1 node. That means, while I am going to construct a BDD, we are going to create an x 1 node. Okay. So, when I am going to create an x 1 node, you just see that this is the scenario that we are going to have. That means, I am going to create an x 1 node. Okay. And here in the low side, what I am going to get? It is coming to x 2, and if x is equal to 0, it is coming to S 4. That means, here I have to create a node. Now, I have to work with this particular node. It is nothing but R 2 S 4, and when it is your solid line, then what will happen? Both are coming to these things. So, what are the work I need to do over here? R 3 S 2. Now, this is the scenario that we are having. That means, now already I have taken decision. Now, we have to work with over here. Now, what node I am going to create over here? You just say this is the x 2 and second one is your terminal node. So, x 2 is coming before that. So, I have to create an x 2 node over here, because it is independent of x 2, 3, 4 in this particular part. So, we are going to create an x 2 node here, and accordingly we will see what we can do actually. And similarly, now when I am coming to these things R 3 and S 2. So, both are x 3 node, then we are going to create an x 3 node and apply the method for this particular part. Okay. Now, because from x 3 we are coming to this particular part. So, here I am going to have the evaluation, because already we have taken a decision on x equal to 1. So, this is the way we are going to construct. So, here x 2 node and here x 3 node. So, finally, we are going to have these things R 2 R 4, R 2 R 3 S 2, then R 4 S 4, like that we are going to have. This is the structure, and these are the nodes x 1, x 2, x 3, x 4, like that. Now, if you see these things, what about R 7, all those things, you see one example R 6 S 4, R 6 S 4, these are the terminal nodes. Now, I am going to apply plus. So, that means 0 plus 0, it will be 0. So, these are the terminal nodes basically. Now, I can apply the operation. So, if I apply the operation, these are the result that I am going to get. So, now you see this is the resultant BDD of after application of this particular apply algorithm, but these BDDs may not be a reduced one. Now, after that we can apply the reduced algorithm to get the reduced BDD, and finally, the reduced BDD is going to have this particular form. So, again it is going to have the same variable ordering x 1, x 2, x 3, x 4. Okay. So, here we can apply or we can perform any operation on BDDs, and finally, we are going to get an reduced BDDs or reduced order BDDs of those particular operation. Now, this is the apply is the main algorithm, and to get the reduced BDD we are having called algorithm reduce algorithm. Here I am not going to discuss about it, but already I have mentioned about the rules how to reduce it. Now, you can look for the implementation of the reduce algorithm. So, now apply is the main algorithm where we can perform the Boolean operation on the BDDs. Now, we are having some more algorithm also, which are going to help is one is known as your restrict algorithm, which is basically the restrict operation. It says that the Boolean formula obtained by replacing all occurrence of x by 0 is denoted by f x 0. That means, I am going to evaluate the function f just putting x equal to 0. Similarly, I can evaluate the function by putting x equal to 1. So, in that particular case, we said that this is the restriction of f. That means, we are restricting the function or evaluation of the function by restricting the values of x to be zeros only. We are least bothered about the functional value when x become 1. Then we said this is the restriction f x equal to 0. Similarly, we can have another restriction where we are going to put the values of x equal to 1. So, now if I am having a Boolean function, I can replace the variable x by 0 and we are going to get the resultant function. So, now if we are already having a BDD representation of the given function, now how we are going to get the BDD after applying this particular restrict operation. So, this is very simple. So, what it says, I can say that restrict 0 x p f, that means, it says that the variable x is restricted to 0. That means, we are least bothered about the here we are going to say that x is equal to 0, we are not considering or we are not looking what will happen when x equal to 1. So, in that particular case what we can say that for each node corresponding to x, because for every variable x we are having a node, we may have several nodes. So, we will remove n from OBDD and redirect the incoming edges to low of n. Okay. So, if this x is there, okay, then x may have, so this is the n, x may have n either 0 or either 1 and several edges may come to this particular point. Then what will happen to restrict it, since now we are going to restrict n is equal to n. So, we are going to remove this particular part, it is redirect to low of n. So, after removing these things, that means, all those edges will go. So, whatever that incoming edges are there, that will be redirected to this particular point. So, these are the incoming edges. So, these incoming edges will be redirected to the low of n. Similarly, for restrict 1 x b f also it is similar way, except that redirection will go to the solid lines. Okay. So, we can do some simple manipulation in the BDDs to get the restricts operation. And there is another operation generally we use to perform. Generally, we sometimes relax the constraint on some variable. Okay. So, it is called relaxation. Basically, if say that if we have some function f on some variable x, y, z like that, sometimes we want to see that we want to relax the constraint on say variable x. We are not concerned about the values of whether it is x equal to 0 or x equal to 1. So, this is the relaxation, we are relaxing these things. So, we relax the constraint on some variable x of a Boolean function x, then f could be made true by putting x to 0 or x to 1. Okay. So, basically what will happen, either x equal to 0 or x equal to 1, we are not considering these things. So, we are going to look both the evaluation and we are going to have the this thing. So, in that particular case, this is the expression basically we are going to have, and we said there exists some x where we are going to relax the constraint. So, in that particular case, the expression will turn up to be like that, because in Shannon expansion how we are going to get x bar f, x is replaced by 0 plus x, f is like that, x is replaced by 1. Now, the constraint is trees mentioning either x equal to 0 or x equal to 1, because x 0 will become this is 1 into something and x equal to 1 is. Now, we want to relax the constraint on this particular variable x. So, from Shannon expansion only we are getting it. So, this says that if we are going to relax on the constraint of x, then the evaluation of the Boolean expression will become these things, f of x replaced by 0 plus f of x replaced by 1. Now, say if we are having the BDD construction of this function f, how we are going to apply this particular relaxation, and this relaxation can be applied repeatedly also. Okay. So, now in that particular case you just see that I know that here I am saying the valuation of x equal to 0 and restrict valuation of x equal to 1. So, x may be either 0 and 1, we are restricting it. So, we are getting 2 OBDDs. Now, we are going to apply this particular plus over here. So, this is basically what we are getting. We are result will be or resultant BDD is going to give us this particular expression. So, we can use this particular apply algorithm to get the relaxation on some variable x, and for there exists some x f, that means we are going to relax the constraint on this particular variable x, then whatever resultant BDD we are going to get, that can be constructed with the help of this particular apply operation. So, these are the some basic operation that we will be needing while going to perform some operation on BDDs, or in particular order BDDs or RO BDDs, reduced order BDDs. And this exist algorithm or that relaxation can be applied repeatedly variable after variable. So, finally, we can apply these things. First, we can relax on x and then some other variable like that. So, finally, we are going to get one expression which will give you the relaxation or functional value of the given function on the relaxation of those particular variables. Okay. Now, I think these are the basic fundamentals requirement to work with the BDDs and to understand about the principle of BDDs. So, what we have discussed basically, we have seen the construction of BDDs, then we have talked about the reduced BDD, then we have talked about the RO BDDs, reduced ordered binary decision diagram, and RO BDDs are going to have a canonical representation of a given function with respect to that ordering or with respect to the ordering that we are considering. Okay. Now, just some question, just see what I am saying. First question, do we get any advantage of using BDD, binary decision tree? We have explained something, we have discussed about these things, you just see whether we are going to get any advantages out of it. May not be, because it is in exponential in nature. Secondly, to get an RO BDD, we need not to start from the BDT, we can start from the Shannon expansion itself. While constructing the BDD, it is required to start from BDT, already I have mentioned, may not be required. The definition of BDD does not restrict the occurrence of a variable in any number of times in a path, so that it may lead to inconsistency with example. I think we have discussed about this issue, now we can look into it. Is reduced BDD of any function is unique? If reduced BDD of any function is unique, answer is no, because to get an uniqueness we have to mention about the ordering of the variables. If you change the ordering, we may get different structure. Already we have mentioned one example. Again you can see another example, that same example that we are having, motivating example that we are discussing over here. So, in that particular case we have seen that if I am going to take function f is equal to a c plus b c, and if we are using the variable ordering a b c, then we are having this particular structure ROBDDs for the given function f. It is the ordering is a, b and c. Now, if I change the ordering, then what will happen? Okay, you can go through it. Now, what is the ordering? First we are saying that we are going to first having an evaluation on b, on evaluation of B I am going to get this function g and h, then on g and h it will be evaluated on C. After having the evaluation of C, then I am going to have the evaluation of A. That means, in this particular construction we are going to the variable, or we are having the variable ordering B, C, A. Okay. So, now after that what will happen, whether can you get these things? Now, you just see that finally, we are coming down to these things after using this particular Shannon expansion. Is there, can you have any scope of reduction over here? No, we do not have any redundant nodes at that particular point. We do not have any duplicate nodes also, because duplicate nodes may be possible with respect to these C's only, because for variable A we are having only one node, for variable B we are having only one node. So, with this particular variable ordering we have got this structure. So, you just see that structure is different when we are applying defined variable ordering. So, RO BDDs are not having a unique representation, but with respect to a variable ordering we are going to have an unique representation. So, if you use this particular variable ordering, always you are going to get this particular structure only, whatever way you are going to construct it. So, ROBDD is having an unique representation. Okay. With this, I will wind up my lecture today. In next class, we are going to see some use of those BDDs, or in particular ROBDDs with respect to model checking algorithm. And finally, we will see the implementation of model checking algorithm, where we are using the BDD representation to represent our system. Thank you all.